1950 DA tsunami, you can see a series of simulations of what happens if you drop it in the middle of the Atlantic. I can't actually tell you where on Earth it would land, because we can plot the line where the asteroid can be. We can plot that line onto the Earth, but I don't know how the Earth will be oriented in space at that point, because the length of the day is uncertain.
What's its chance that you need it?
It's about 1% in the current assessment.
1%? Less than 1%?
We're not sure if it's somewhere of that order. Maybe we're quantifying our ignorance here. Ideally, we'll rule it out completely. It won't be a problem anymore. But we need more data.
I'm hoping for tax day. So, even at these low densities, why would you not just land a rocket object, a rocket on it with perhaps a dish-sized contact plate, if you will? Why would you not just push it?
It is a pile of rubble, and you put a rocket engine, press it into the surface, it's not clear how it reacts. So I mentioned the asteroid redirect mission, which was a NASA proposal. The idea there was to pick up a block from the surface of a near-Earth asteroid, something that might probably fit on this stage, and bring that back to Earth. One of the big engineering challenges there was how do you design a system to grab on to a large block that's several tens of tons and move it around space in a controlled way with a rocket. Moving around the entire rubble pile as opposed to a block that has a certain degree of cohesion, that becomes much more difficult. The gravity tractor has the advantage that it just pulls everything uniformly. Question here.
I was wondering if you have to destroy the satellite.
So I talked about how we have to, this is for the kinetic impact deflection, why it has to get destroyed on impact.
Yeah.
So I talked about how we need as much momentum as possible. Momentum is the product of mass and velocity.
Okay.
So if I want to move a asteroid that is 10 million, 100 million times more massive than my spacecraft by a certain amount, I need my spacecraft to be traveling 10 million times, 100 million times faster. So if I want to move the asteroid by a millimeter a second, I need the spacecraft to hit the asteroid at 10 kilometers per second, 6 miles per second. It is very, very hard to make a spacecraft that can survive running into a mountain at 10 kilometers per second.
Yeah, I can understand that. Anyways, no, it's not.
People have talked about designs for impactors that actually survive the experience, but it's a very hard problem.
This is maybe going a little afield. As you are mapping all of the paths of these asteroids, has anyone thought about using them as shielding for missions manned missions to the outer solar system? Because if you could park your spacecraft in the shadow of one of these close approach asteroids for the portion of the mission when you're close to the sun, or close to Earth, you could ride that shadow out to where your shielding issues are less, and you don't have to launch as much mass off Earth to use as a shield for the manned mission.
There is a whole separate talk about space resources and near-Earth asteroids, which I didn't have time for tonight.
Okay.
There are several different companies and space agencies working on this, and I talked about how asteroids contain lots of water and carbon compounds. People talk about using those for life-supported fuel. But one of the other primary products is just pure mass. You take all the rubble pile that you don't have any other use for, you pile it into sandbags, and you put that on the outside of your spacecraft for radiation shielding for humans' sensitive electronics. So it's been talked about, and there are companies working on it. I just didn't have time to talk about it tonight.
What is the current estimate as to when it is thought that humans could go to Mars?
I am not that sort of engineer. And I wanted to predict what investments people will make in space in that particular set of spacecraft.
Hello. What?
Last two questions, please.
What's the possibility of mining an asteroid?
So that's the space resources stuff that I talked about. People talk sometimes about mining asteroids for platinum, because I mentioned iridium, which is a platinum group metal, and mixes in with the iron. And you have also platinum, palladium, and so on. that is actually not valuable enough to be worth mining in space and bringing back to the ground. Instead, the products are stuff to be used in space. So you pull water out of asteroid material, you can use that for fuel, for life support for humans. You can pull carbon compounds out, make plastic, make composite material, potentially life support. You can talk about using nickel iron asteroid material for making structural elements. If you want to get really fancy, you can make solar cells out of the silicon, but that's a separate topic. All right.
Michael, thanks for the talk. And I'm glad you touched upon the space resources side. So we didn't only explore the dark side, if you will, of NEOs. And yeah, we should talk to Andy about organizing another talk on the other side of the coin, the space resources side. But a question, you know, when we did the FDL workshop and we talked about these mitigation strategies, we had the gravity tug and the kinetic impact. There was a third one, which you didn't touch upon tonight, and I wonder if that is now, for some reason, off the table, or just didn't want to talk about it as too controversial, but that's the nuclear nudge, if you will. Can you comment on that?
The project here that Bill was describing was the idea originally developed in the 1990s that you would deflect an asteroid by setting off a nuclear bomb. This is overkill for these smaller asteroids. So you don't actually blow the asteroid to pieces. You don't want to do that, because then you have rubble pile bits going every which way. Instead, you set off the nuclear device a few hundred meters above the surface, and the flash of X-rays and gamma rays vaporizes that whole side of the asteroid, and that gives you a shove on the rest of the mass. Megan Brooks-Sile over at Livermore, among many other people, can tell you in detail how that would work. For the smaller asteroids, we've got lots of warning time. It's not necessary. The kinetic impactor and the gravity tractor can do the job without the complexities of such explosives. And also, we're not going to test that ever, because there's international treaties that say we're not going to put nuclear bombs in space. I want to make one final comment, if I may, because I forgot to highlight it during my talk. I want to emphasize just how international and collaborative all of this asteroid stuff is. So you see here all the different space agencies that have been involved in asteroid missions. We have NASA, we have JAXA, the Japanese Space Agency, we've got the European Space Agency, we have the Canadian Space Agency, the Chinese Space Agency, and that's not including the many other countries where people who contribute to asteroid survey and characterization are based. Australia, Chile, do lots of stuff in the southern hemisphere, South Africa, and many other places, because we want to cover as much of the sky as possible and find asteroids in all directions, and then also keep tracking them no matter where they go on the sky. So this is an international and global project by necessity. All right, thank you all again.
Everyone. My name is Andrew Krakauer. I'm the Emeritus Professor of Astronomy here at Foothill College in Los Altos Hills. And it's a great pleasure for me to welcome everyone here in the Smithwick Theater and everyone watching us on the web to this program in the 18th year of the Silicon Valley Astronomy Lectures. These lectures, free of charge for everyone here locally, are made possible through the support of 4 organizations that do public outreach in science: the Ames Research Center of NASA. NASA is one of NASA's premier centers in the country, NASA Ames, and the Foothill College Astronomy Program, which offers day and evening classes in astronomy, the Venerable Astronomical Society of the Pacific, the College Organization of Astronomy, and the SETI, Search for Extraterrestrial Intelligence, SETI Institute in Mount we're very grateful for their support. Today's program is one I'm especially looking forward to. We're very lucky to have with us Dr. Ashwin Vasavada. He is a planetary scientist at the NASA Jet Propulsion Laboratory in Pasadena, California. And we're very grateful to JPL for making him available to our program. His research interests include the climate history of Mars, the weather on Jupiter and Saturn, and boy, is there weather on Jupiter and Saturn, the possibility of ice at the poles of the Moon and on Mercury. Currently, he is the project scientist for NASA's Curiosity rover that began development in 2003 and successfully reached Mars in August 2012, sending back amazing images and data about the red planet. He now leads the international team of scientists as they explore Gale Crater on the Martian surface. We are very, very fortunate to have him with us today. So let me present to you Dr. Ashwin Vasavada talking about when Mars was like Earth, 5 years exploring with the Curiosity Mars rover.
All right. Good evening, everybody. It is wonderful to be here, and thank you so much for spending the evening